everyone. My name's Keone Han, co-founder of Monad. My goal for today is to talk about two specific concepts within the Monad design: asynchronous execution and parallel execution, both of which I think are really important for making the EVM a lot more performant. So I'm from Monad, and I guess a couple of objectives for today are to explain what is Monad from the user's perspective, and then additionally to explain some of the performance improvements under the hood that help deliver the characteristics that we see from a user perspective. Okay, first of all, what is Monad? So Monad is a fully EVM equivalent layer 1, offering really high performance over 10K TPS, aka a billion gas per second, with 1 second block times and single slot finality. Additionally, Monad has full Ethereum RPC compatibility, so you could use all the same infrastructure like Phantom Wallet or MetaMask or Etherscan, the Graph, Alchemy, etc. So from a user perspective, Monad is really offering the best of both worlds between performance and decentralization. So existing apps and infrastructure can work on Monad without any bytecode changes, and in addition, it's really cheap to run a node, and we can get really high performance, which then translates to really low cost. And lastly, Monad is really decentralized because these performance improvements are allowing hundreds of nodes to participate in consensus from day one, and reasonable hardware requirements. So I think from a user perspective, what users care about is both performance and decentralization. Like, that is why we are all here, is because we care about decentralization. It's really important to preserve that. Now, from the developer perspective, Monad is offering the best of both worlds between performance and portability. So we kind of have a trilemma that's, or a three-sided triangle that's developing here: performance, decentralization, and portability. So from a developer perspective, you could use any contract without any changes. It doesn't even need to be recompiled. And I think some implications of this performance really are not only that it's a lot easier for users to onboard and use and not have the frictions of high gas, but also from a security perspective, there are a lot of implications, because at the end of the day, I think one of the biggest impediments to users using decentralized tech is all of the hacks that keep happening. And the benefit of high performance is that we have really cheap gas, which means that developers can write code without having to take on arcane gas optimization. So it really sort of shifts the calculus for a developer. They don't have to worry about gas optimization nearly as much, can write many more defensive assertions that make sure that invariants are preserved and ultimately protect the user funds that are deposited into smart contracts. All right, so how do we get this? So the first part of this was really just to explain at a high level what is the consequence of various improvements. But now I want to explain how this is possible. So the fundamental constraints or fundamental resources that any blockchain designer is trading off: network bandwidth, CPU throughput, state access, aka SSD throughput, and state growth. These are just fundamental constraints that any blockchain designer is running into. And I think something to keep in mind is that there's a temptation perhaps to put the finger on the scale and just basically cheat by raising bandwidth requirements in the case of the bandwidth constraint, or putting all the nodes in the same geography. And then from a state access perspective, it's very tempting to raise the RAM requirements on nodes that are running the blockchain. But the consequence of this is a huge effect on decentralization, because then it becomes very hard for normal everyday users to run a node. It becomes more expensive to run a node, which then messes with the economics of the network. It's really just important that anyone should be able to run a full node and fully verify all transactions and have access to this full state of the world. So how do we do that? Like, how do we get high performance without compromising on decentralization? What we need is new software architecture that can deliver the best of both worlds. So the goal of Monad has always been to use commodity hardware, like basically to be a network that you could run on a MacBook Pro that you get from Costco. preserve decentralization, have reasonable RAM requirements, be fully geographically decentralized, with hundreds of nodes participating in consensus. And in order to do that, we need new software rather than more hardware. So new software or new architecture, what does that entail? So there are 4 major improvements within the Monad design. I'll just mention them really briefly. Monad BFT is performant BFT consensus. Number 2 is asynchronous execution. Number 3 is parallel execution. And number 4 is MonadDB, which is delivering performance state access. And really for the purposes of this talk, given the constraints of time, I'm going to be focusing on the second and third one, asynchronous and parallel execution. So first of all, asynchronous execution. Just as background, Ethereum and most other blockchains have linearly ordered blocks with linearly ordered transactions within a block. And in most blockchains, the consensus and execution components are interleaved with each other. One thing to keep in mind is that consensus is quite expensive because it involves round the world communication, like nodes on opposite sides of the world talking to each other. So the reality is that in most blockchains where consensus and execution are interleaved, the budget for time is very much squeezed for execution. There's a very small portion of the block time that can be allocated to execution. So an analogy I always like to use is, have you guys seen the movie Limitless? I guess, could I get a show of hands if you've seen the movie Limitless before? Okay, cool. So a couple of people. It's actually a really good movie. Definitely recommend it. But the premise of the movie is that the aphorism that you only use 10% of your brain, that there's this pill that someone can take that allows them to use 100% of their brain. And so this guy gets access to these pills. He takes it. He becomes OP, like he's crushing it. And then, of course, there's some problems that arise with that. And then the narrative arc of the movie swings to the hard part, and then maybe it gets resolved. But the point is that it's very tempting to imagine this idea that there's this pill you could take that would make you able to use 100% of your brain. The exact same thing is kind of true here. So in Ethereum, we have 12-second block times, but the actual time budget for execution is roughly 100 milliseconds. And that's crazy because that's less than 1%. So kind of what's happening in blockchains where consensus and execution are interleaved is that execution is only getting to use quote unquote 1% of the brain. And what we'd like to do is to be able to make a change so that we could use 100% of our brains. So if hopefully that piques your interest a little bit about this magical change we can make to enable this. I'll explain it in really simple terms now. So what we have here is a diagram of interleaved execution. Execution is represented as the dark blue rectangle, and consensus is represented as the light blue one. And so in blockchains where you have interleaved execution, it just progresses like one after another. Execution first, then a round of consensus to finalize the block, and then start on the next one and keep going like that. And here's a schematic diagram of the work being done over time. Blocks are the y-axis and time is the x-axis. So in asynchronous execution, what happens is we actually move the execution out of the hot path. So nodes will simply come to consensus about the official ordering of transactions without executing at all. Then 2 things are going to happen in parallel. There's 2 separate swim lanes. The first is that we'll start executing on that list of transactions that's just been consensused upon. And the second thing is we're going to have consensus on the next block. These happen in parallel. So that's pretty much the nature of asynchronous execution. It is a change to move execution out of the hot path into a separate swim lane. Here's its updated schematic of this new kind of thing. You can see execution is now after consensus. And this is a slight, if you kind of compare these 2 side by side, they look pretty similar. There's a slight improvement because now we can start consensusing on block number 2 before any work is done on execution for block number 1. And so I've kind of drawn some dotted lines to show like what the effect was there as a little bit of a speed up. But if we kind of zoom in on this a little bit, we'll notice something kind of cool, which is that now because execution is out of the hot path, there's actually the potential to increase the size of that dark blue rectangle substantially, aka have bigger blocks with more transactions in them. And that's literally the unlock that asynchronous execution gives you, is it allows the system to commit to a large amount of work through consensus without having done any of it. And then as it moves on to the next block for consensus on the next block, then execution can run in parallel on that previous block. So we have a much larger time budget for execution. So this is the limitless change. This is the change that goes from 1% of block time to 100% of block time in expectation. Now, just to point out a couple of consequences of this. So the first thing is that now we have nodes coming to consensus prior to executing, which means that they're working on building blocks without a fully updated state of the world. And so you might worry about spam attacks where someone, submits a bunch of transactions from an EOA that's actually empty, that we don't know is empty yet because we don't have an updated view of the state of the world. And we have a subtle way of how to address that problem. Similarly, the nodes are coming to consensus with a slightly delayed view of state, and they're each computing execution results independently. So you might worry that one of the nodes got hit by cosmic rays and has made an error in computation. And so we have a way to address that problem as well. I can address it in the questions if it's of interest. And just to point out one final thing, finality is a consensus time. So if there's agreement about the official ordering of transactions, then the state is deterministic, and therefore finality is at that consensus time. Okay, so now we're moving pretty quickly here. So the other improvement that I want to talk about today is parallel execution. So Monad does optimistic parallel execution. The goal is to preserve linear ordering of transactions and linear blocks, but then do work in parallel in a way that is just smarter. We can get more done while still actually having the truth value, like the true state of the world, be as if the transactions have been run serially. So kind of 4 bullet points for how optimistic parallel execution works. The first one is we're going to run many transactions in parallel, assuming that they're starting from the same starting point. So when we say it's optimistic parallel execution, the optimism is referring to the fact that these transactions are assumed to be starting from the same state of the world. This is totally different from like the optimistic rollups. So that's a common point of confusion, but optimism here means assuming we're starting from the same state of the world when many transactions are run in parallel. Okay. The second thing to know is that when all of these transactions are run in parallel, we generate pending results for each of those transactions. So pending result basically means we just do a bunch of bookkeeping to keep track of all of the pieces of state that were inputs to that transaction and all pieces of state that are outputs from that transaction. So an input just means a piece of state that was read in, i.e. the S load, opcode, and EVM. And every output is a piece of state that was mutated, aka the S store opcode. And just to point out, that means that bookkeeping is being done on a slot by slot basis, not on a contract by contract basis. So generate a bunch of pending results for each of those transactions that were run in parallel. Then the third thing is those pending results are stepped through and committed in the original order of the transactions. So this is how optimistic parallel execution preserves the same result as if the transactions have been executed serially, because they're actually being committed serially. And then lastly, there's the job of, for each of those pending results, it's committed in order, and the inputs are checked to make sure that they're still valid. And for any pending result whose inputs have since mutated, that transaction is thus re-executed. So re-execution happens only if needed, but it's there to preserve correctness as if serial execution had happened. Okay, so I think the best way to really understand this is just to go through an example. So I'm going to do a really simple example, which is, let's say that the initial state of the world is that I have 1,000 USDC and Dorothy has 0 USDC and YQ has 300 USDC. So apologies, I should have updated these slides, but just to keep it a little more relevant. So I have 1,000, Dorothy has 0, YQ has 300. And then we have 4 transactions that are happening in parallel. The first one is me sending Dorothy 100 USDC. The second one is some unrelated transaction, someone minting an NFT. And then the third transaction is me sending 100 USDC to YQ. Okay, so let's assume that that's the list of transactions that's going to be executed in parallel. So can anyone tell me what the state of the world should be after these transactions are executed if we were just doing it normally, like in a serial fashion? What the balances should be? Okay, so what should my USDC balance be? I just yell it out, it's okay. Yes. You said 900. That's actually not right. 800. Okay, yes. So 800 is right because I start with 1,000 and then I spend 100 twice. Yeah. Okay, and then cool. And then what should it be for Dorothy? Anyone yell it out? 100, yes. And then what should it be for YQ? 400, yes, that's right. Cool. So there's just a little check to make sure that this is what result we should get. Now let's talk about what happens when we do optimistic parallel execution in this situation. So as I mentioned before, optimistic parallel execution means running a bunch of transactions at the same time, as initially assuming they're starting from the same starting point. So what'll happen is transaction 1 and transaction 3 are both run, and when the state is read, it's going to read in my account as having a balance of 1,000 USDC. And then it's going to say that Dorothy has 0 and YQ has 300. And then it's going to generate outputs for transaction 1, me going to 900 and Dorothy going to 100. And then for transaction 3, again, because it's being run in parallel, it'll say that I go to 900, from 1,000 to 900, and YQ will go from 300 to 400. So obviously there's something wrong here, but what's going to happen is just the intuitive thing. We're going to step through these transactions one by one and make sure that the inputs are correct and commit them if so. So we're going to get pending result 1. We see that it starts with 1,000 and 0, and those are both still correct, so we can commit this one. The second transaction is some unrelated thing, so that gets committed fine. And then we get to the third pending result. Now we see that the inputs for that pending result are wrong because it assumed that I started with 1,000, but I actually have 900 now. So this would need to be re-executed. So when we re-execute it, then I start at 900 and I end at 800, and now it's fine. So that's literally all that optimistic parallel execution is. And I know that there's a lot of fancy names for this algorithm like STM and optimistic concurrency control. But it is really just literally doing the intuitive thing of doing some bookkeeping, doing work in parallel, and then committing. So it's a 2-phase process. The first phase being the parallel part, and the second phase being the serial part for commitment. But it is an intuitive algorithm that everyone should be able to understand. Okay, so just to point out a couple of things, if a transaction has to get re-executed, it'll happen at most once because a transaction will get run once in parallel, and then it might have to get run a second time upon re-execution. So people sometimes worry that we'll get into infinite loops or something. That's not possible because every transaction by definition will be run at most twice. The other thing to point out is that people often worry about the cost of that re-execution. They worry that there's going to be 1,000 transactions that are all serially dependent. And that's true, that could happen. But the good news is that re-execution is actually very cheap in most cases. And the reason for that is because the cost in execution is mostly state access. It's not compute. Compute is actually very, very cheap relative to the cost of reading some piece of data from SSD. For context, reading data from SSD costs between 40 and 100 microseconds every single time you go to the SSD. And the good news is that on re-execution, that state is usually in cache, so it's just a memory lookup. It's much, much faster. All right, so I've kind of talked about 2 things that Monad is working on very quickly. I guess just to point out, the sort of takeaways from this talk. There's a number of open research problems we're really excited about. I'll mention some of them here. Given the constraints of time, I'll probably just let you read them. Oh, we have 5 more minutes. Oh, wow. Okay. That's new news to me. But yeah, I think more generally, my hope is that with Monad, it's a way to explore some of these architectural improvements, and ultimately my hope is that some of these improvements get upstream back to Ethereum. So we'll make proposals as EIPs. Have not done that yet because we need to open source the code, and we're still working on some things. But yes, the goal is ultimately for Monad to be a vanguard environment for pioneering EVM improvements, such as these two that I talked about, as well as others. Just in terms of open thoughts, I want to point out that the biggest bottleneck for state or for execution is actually state access. And so, although I didn't talk about it in this talk, MonadDB is an effort that that our team has been very focused on to deliver performance state access, because you can have parallel execution, which means that many transactions are being run in parallel. And we have that nice optimistic algorithm for making sure that we still get the same end result when we do run transactions in parallel. But at the end of the day, if there's still a state bottleneck, like every single transaction has certain dependencies that need to be pulled from disk, it is ultimately comes down to the performance of that database as well that's storing all of that state. And with MonadDB, MonadDB is an effort to store Ethereum Merkle tree data natively on disk. Again, it's not really in these slides given the constraints of time, but Monad is very much focused on delivering efficient Merkle tree storage. And so one interesting arc is that people are exploring Merkle trees, and I feel very strongly that Merkle trees are the way to go, because the overhead of maintaining state in the Merkle tree is substantial. Anyway, actually, let me just open it up for questions. Let's see if anyone wanted to ask about anything. Yes.
Yeah, I guess between the asynchronous execution, parallel execution, as well as the Merkle tree DB optimization, which one is the biggest contributor to your performance improvement? At what ratio? Roughly?
Yeah, that's a great question. So one thing to point out is that with these different improvements, the question was which is the biggest improvement between asynchronous execution, parallel execution, MonadDB, and even the other improvements. So the cool thing about these improvements is they actually stack. It's a multiplier effect just due to the nature of these improvements. So asynchronous execution is about giving yourself a bigger time budget to execute in. And then optimistic parallel execution is about doing as much work within whatever time budget you have been given. And MonadDB is really about getting access to the state most efficiently so that each individual transaction can progress a lot faster. Go ahead. Did you?
Sorry, I guess, is there any metric you can share with us?
Oh, sorry. Well, I think not at the moment, but I will later. The main thing to keep in mind right now is that asynchronous execution is probably the biggest improvement, because it's literally changing the amount of time that we have to set as the time budget. It's a substantial improvement from going from needing to constrain execution to a tiny fraction, like 1% of the block time, versus being able to use the entire block time.
Thank you.
Actually, I have a quick question. Sorry.
Awesome.
So one thing is like, so I know like Monad and Keone, you building the whole thing for years. Like, in theory, roughly in your mind, is there any like theoretical limit for the like sort of this Monad? I mean, once we launch testnet Monad.
Yeah, the theoretical limit is kind of around two things. One is the throughput of the consensus mechanism, given the bandwidth constraints that we've chosen to embrace. So if you change those, then it's possible that could be raised. Right now, what we're seeing from our tests is over 10,000, like somewhere between 10 and 15,000 TPS of throughput, given the constraints that we've imposed, which is 100 megabit bandwidth, fully distributed. The second constraint is really around the actual state access. So SSDs offer about 1 million IOPS, 1 million IO operations per second, and then within that there's basically like a number of IOPS needed to do one lookup because we need to traverse through the Merkle tree. So there's some theoretical limits around like how much bandwidth we can get out of the SSD, how many transactions we could process out of the SSD.
A quick follow-up one is like because once we know the theoretical limit, so we know that Monad will be a decentralized network, right? You also had the debate on the full node definition. So like then do you have any like sort of optimizations and what kind of these specs you require for like sort of community members or some project to run the full node for Monad in the future? Yeah.
Your question is like
Optimization for full node.
Oh, I see. Well, at the end of the day, a full node is very similar to a validating node in the Monad design. It is just a matter of whether they're like sending consensus messages, voting directly, as opposed to just listening to the traffic. So, not too much of a difference there.
I see. We can have one more.
Hey, so my question is, I've heard that most of Ethereum bottleneck is about state growth and like the block size being designed for nodes, having decent storage. And like I think Ethereum state right now is around 300 gigabytes with I think 2 billion transactions being processed in total on mainnet. What do you think about Monad state growth with 10,000 transactions per second? And like, is there any plan to improve state growth on that end?
Yeah, so two things there. This is a great question. Yes, at the end of the day, one of the concerns about state growth is really the high cost of doing a lookup from the Merkle tree, and also that cost increasing as time goes on, as the state gets bigger and bigger. So I think with MonadDB, there's been a substantial improvement to the cost of doing one lookup. Again, we didn't really talk about it here in this, but it changes the calculus a little bit in terms of how big we think that state can grow while still delivering very reasonable lookup times. So with MonadDB, we've tested up to several billion keys. I think right now Ethereum is about 250 million keys. But there's the potential to scale to like a much larger version of Ethereum state without concerns. The second point I want to make is that you're right that at the end of the day, the state growth is just literally, like it's almost tautological. Like if you have 10 terabytes of state, then you have 10 terabytes of state. There's no it's just you're going to need a 10 terabyte hard drive. There's no way around that. So I think that in the longer term, there may be some adjustments needed in terms of cost of different opcodes. So I mentioned this on this slide that on day one, Monad will just preserve the same relative costs for different opcodes. But in the future, it might be true that like an S store from a 0 to non-zero slot, like that might be higher price than it is right now relative to some of the other things that are more transient in nature. And that's just really economic forces to push people toward cleaning up state that they don't need. Or like if you're building an order book, like making sure that the order book, like new orders, when they get canceled, they don't like leave residual state, they get cleaned up. But yes, I totally agree that the state growth, and the last point I want to make is that having 1,000x the throughput doesn't necessarily mean 1,000x the state growth. Like you might be enabling a lot of things which are just doing a lot of transient state changes, such as an order book.
Thanks.
Okay, great. It's an amazing talk from Keone on Monad. And let's give another round of applause for Monad.
Okay, thank you so much for having me.